Hello everyone, my name is Mauricio, and together with my partner Anderson, we're going to talk about data cleaning techniques applied to a real dataset. The dataset we chose for this project comes from NASA. It's a publicly available catalog of exoplanets, basically planets that don't belong to our solar system. These planets have been detected by astronomers using various observation techniques over the past 3 decades. The main values or columns in this dataset that we'll be going through are the name of the planet, the type of the planet, which classifies it either as a gas giant like Jupiter, a Neptune-like planet, those that have cold and windy atmospheres, a super Earth, which basically means planets that have a mass bigger than Earth's, or a terrestrial planet, planets that have the same conditions as our home. The other key columns were the detection method that tells us how the planet was found and the year it was discovered. The dataset also includes columns for the mass of the planets, the radius, the orbital radius, which were really not the focus of our analysis. The key columns are the ones I mentioned before, and the other ones really just served a purpose for calculations and drawing conclusions later on. But really, the goal of our project was to bring a real-world dataset which is rarely perfect and comes with missing values, incorrect data types, duplicate entries, into a state where it is consistent and complete in critical fields, and basically ready for an analysis. Specifically, we identified the following problems in the data. First, several columns had the wrong data type, such as the distance, the orbital period, and the mass had text loaded instead of numbers, which made any calculations impossible. Secondly, some rows were missing either the planet name or a detection method. And finally, there were duplicate and invalid values. Some planets had duplicate entries, and some values like orbital periods were equal to 0, which is not physically possible. With those problems identified, we applied the following data cleaning steps. First, we fixed the data types. We used the toNumeric function to convert any value that cannot be transformed as a number into a NaN field instead of crashing the entire program. Then we dropped missing values using the drop NA on the name and detection columns, removing any row that lacked these two fields. Thirdly, we removed duplicates using the drop duplicates function on the name column, ensuring that a planet only appears once in the dataset. And finally, we filtered invalid values. We kept only planets with a discovery year of 1990 or later, since earlier entries tend to have incomplete data, like the one I mentioned before. Moving on to the transformation, having our clean dataset, we decided to split them into groups based on the detection method. Planets discovered using the transit method and planets discovered using any other method. The transit method is when we look at stars and the brightness they emit, and basically if that brightness ever lowers, it means that a planet is passing in front of it from our point of view. That is what the transit method consists of. We added a new column called group to each subset to label them, and we used the function concat to bring them back together into a single data frame. The result is identical in content to the original dataset, but now carries another label for each planet indicating which detection group it belongs to. We then created a separate reference table containing a description of the planet and the size range for each planet type. We then merged this reference table into the main dataset using planet type as the key.
Now that we have cleaned and transformed the dataset, we can start analyzing the visualizations. This first chart shows the distribution of planet types across the cleaned dataset. As we can see, Gas giants dominate by a very large margin, representing more than 80% of all confirmed exoplanets in the dataset. Neptune-like planets are the second most common category, followed by super-Earths. Terrestrial planets, which are the most similar to Earth in size and composition, are actually the rarest group in this dataset. This also reflects an important detection bias, because larger planets are much easier to detect with current technology. This chart shows how many planets were discovered using each detection method. Radial velocity is the most common method, accounting for nearly half of all confirmed planets. This technique works by detecting the small movement or wobble that a planet causes in its host star. Here we can also see the importance of concat function, because the dataset was divided into transit and non-transit groups before being combined again. We were able to compare how many planets were found by each method while still keeping everything in a single dataset. This chart shows how exoplanet discoveries changed over time. Before 2008, discovery rates were relatively low. Starting around 2009, the number of discoveries increased significantly due to improvements in telescope technology and dedicated space missions. The highest number of discoveries appears in 2022, which reflects the growing ability to detect and confirm candidate planets. Again, thanks to concat function, we could preserve the detection group information and analyze not only how many planets were discovered each year, but also which methods were responsible for those discoveries. This chart compares orbital periods between different planet types. Most planets in the dataset complete their orbit in less than 50 days, meaning they orbit extremely close to their stars. This is another example of detection bias. In short-orbit planets are easier to confirm because they pass in front of their star more frequently. This visualization was improved using the merge function. The original dataset only contained the planet type names, but after merging a reference table using planet type as the key, we added descriptions and context to each category. To conclude, the cleaning steps ensured the data was consistent and reliable. The concat function let us restructure the data by grouping rows with a meaningful label, and the merge function let us bring in external information and attach it to each row using a shared key. The visualizations were only possible because the data was clean. A dirty dataset would have produced misleading charts. This is why transformation always comes before visualization. The quality of your analysis depends entirely on the quality of your data.